Welcome. What we're going to look at now is basically what happens when you have one light, you put it together with another light. What do you get? Two lights. We have two lamps, which when you switch them on, one after another, we shine them at the screen, and what do we get? First light comes on and the screen is illuminated. Perfect. When the second lamp comes on, you would expect the screen to be twice as brightly illuminated. But what happens is this. When the second lamp comes on, the screen has some areas where it's very bright, but some where it's very dark. The intensity is zero. The light kind of disappears in these spaces, and these are called Young's fringes. This can only be explained using a wave model. So here is an example of the wave model. We have two waves here. We have the crest of one meeting the crest of another. This displacement, which is a positive displacement for each, they add up and together they get basically a double displacement. So we get constructive interference, we get a double amplitude. On the other hand, if they meet and one crest coincides with a trough of another, they're basically out of phase, and we have one positive displacement, one negative displacement. We add them together and it adds up to zero. So this is destructive interference. So we have to basically say that when two or more waves meet and overlap, the resultant displacement at any point is the sum of the displacements due to each individual wave. So here again we have a double amplitude there, two crests meeting, we basically get a double amplitude. When we get the crest meeting the trough, this basically cancels out. We get destructive interference. Now we have to be able to derive an equation which shows this. Here we have two sources of waves, but we can treat them as light. We can treat them as apertures or gaps in a barrier where light is passing through. Each aperture can be treated as the source of a new wave. So the light from this aperture and this aperture meet at the point there. The distance travelled from each point is exactly the same, so there's no path difference, so they're going to be in phase. One crest will meet the crest, the trough will meet the trough. We get a double intensity. Slightly to the side, however, you notice that the left beam has travelled less than the right beam. In fact, it's the right beam that travels further by half a wavelength. So what happens here is that the path difference is half a wavelength. This destructive interference accounts for the dark fringe, or for the zero intensity in the Young's fringes. To derive the formula, we need to consider two fringes of maximum intensity. In other words, when the waves are in phase. So let's draw this again. This is the maximum intensity here. We've got two rays of light that are in phase. So the distance travelled is the same, no path difference. And here again, that we have constructive interference basically because the beam from the right has travelled one wavelength further than the beam from the left. So the path difference is 1 lambda. And here we need to look at the geometry of the situation. We call the distance between the slits, or the distance between the sources, as being d. We draw the perpendicular to the right beam. So d is the distance between the slits, and theta is the angle of first constructive interference from the center. This is the perpendicular, this is the angle. Now this has travelled n lambda, and on this side it's n lambda, but in the bottom right hand corner here we have n lambda plus another lambda there. Let's look at the geometry of this triangle. This is theta, the opposite side is lambda, this is the opposite side is lambda, the hypotenuse is d. So we can say that the sine of this angle is lambda over d. let's zoom out from this and see what happens if we see the interference on the screen, if we see the Young's fringes on the screen. The light from the fringes is interfering constructively there, and you can see we've got a bright fringe there. We also have a center fringe where we have constructive interference too. So the fringes are projected onto the screen at a distance capital D from the double slit, and the distance between the fringes is S. Here's distance S, and here's distance D. Let's look at this triangle. What is the geometry of this shape? The sine of the angle is opposite over hypotenuse, so the sine of this angle theta is equal to S divided by D. But hang on, D is the adjacent side, not the hypotenuse. However, this triangle is so narrow that the hypotenuse and the adjacent side are basically the same length, so we can treat them as being equal. And this is the same as the same sine theta that we had in the previous slide, which is equal to lambda over d. So we can equate these. S over d is equal to lambda over small d. Rearrange. Make S the subject. So S is equal to lambda capital D divided by small d. And this is how it appears in the data booklet. And here it is in the data booklet in the right section. Now, as an afterthought, I have a question for you. Can we make cats do this? Can cats interfere? Can you get fringes of cat and no cat? Here's cat 1 and here's cat 2. Can we get them to interfere? He thinks not. And nor does he. Can cats interfere with themselves? Now, can this cat interfere with this cat? I wonder.